what we're going to do is we're going to set up 78 first. So 78 and 79, and this is lesson assignment 33. They're both two-dimensional collisions. So let's read the problem and then we'll set it up. So 78 says a 1,000 kilogram car, so I'll call that A, is moving at 25 meters per second, so the velocity of A is 25, in the positive y direction. So it collides perfectly inelastically with a 15 kilogram car, 1500, moving at 20 meters per second in the plus x direction. So first of all, the main thing here is momentum is a vector quantity. It has both magnitude and direction. So I'm going to draw a picture representing these, the vectors. So momentum of A, it's going the positive y direction, which is up. So this vector represents PA, which I know is MAVA. Now, then the other one is going in the positive x direction. So I'm drawing my vectors head to tail. So this is going to represent PB, which is MBVB. So then the question says, determine the magnitude of the system's resulting velocity and the direction. So this is the momentum of A before collision. This is the momentum of B. To find the resultant, because they're going to stick together, it's perfectly inelastic, I'm going to find the resultant by adding my vectors head to tail. So this is where I start, and then this is where I end up. So it's important to draw the arrows correctly. Where I start is the tail, and where I end up is the head. So this is PA, this is PB. This vector is going to represent the combined momentum P prime. Now, in order to find P prime, this is what? This is a right triangle. I can find PA and PB, those two sides, just by multiplying using the definition of momentum, P is equal to MV, but I'm not going to do the math now. And then I can find P prime. To find P prime, I'm just going to use the Pythagorean theorem. So I'll use the Pythagorean theorem to find P prime. And that's it. But the question said to find the velocity. So because I want to find the velocity after the collision, my definition of momentum is mass times velocity. After the collision, my momentum is P prime. My mass is the combined mass of MA plus MB, and then I want to find V prime. So if I rearrange this, the velocity would be P prime over MA plus MB. And then when I want to find the angle, you always measure the angle from the tail of the resultant. So it would be easiest to do it in the triangle. Okay. So if I want to find this angle, I know opposite and adjacent. So to find the angle, I would end up saying tan of theta is opposite over adjacent, which is PB over PA, and that's how I would find the angle. So that's the simplest type of two-dimensional collision. So it all has to do with your diagram and understanding vector. So that's 78. All right, now we're going to look at 79. 79 is a little bit different. So 79, the first thing I'm going to do is I'm going to draw my picture. So I have one mass like this, I'm going to call A, and it's moving with a certain velocity. So this arrow is representing the momentum of this first ball, because if I read the problem, it says a 0.5 kilogram ball moving at 7 meters per second. So PA represents this. In the positive x direction, it hits a stationary 0.4 kilogram ball, so this is MB. After the collision, the 0.4 kilogram ball moves at 5 meters per second at an angle of 37 degrees below the horizontal. Determine the velocity, magnitude, and direction of the 0.5 kilogram ball after the collision. In physics, the main thing that you first learned was you always have to have a frame of reference. That's the first thing that we learned when we started physics talking about one-dimensional kinematics, and the same thing with momentum. So what is our frame of reference? Our frame of reference is the original direction of this ball. So after the collision, they told us that the second ball, MB, goes off this way, the 0.4 kilogram ball. So this represents PB prime, and they told us that this angle here was 37 degrees. And then the other one is going to go off this way, so this vector represents PA prime. And then this was, I think, 53 degrees. So now, conservation of momentum says the total momentum before is equal to the total momentum after. So let's look at our pictures here. This vector here represents the total momentum before. These two vectors here, added head to tail, represent the total momentum after. So what I'm going to do is I'm going to draw what's called a momentum triangle. So the total momentum before is PA, and that's equal to MAVA, which I can easily calculate. The total momentum after are these two vectors added head to tail. So this is where I start. So I'm just going to look exactly like my picture here. This is going to be PA prime. From the head of that vector, I do the tail of the other. This is PB prime. So if I know these angles here, and this is a right triangle, if I know the hypotenuse of this right triangle, and I know the angles, can I find the other two sides? Definitely. So I'm going to use sine and cosine or whatever I want to find the other two sides. After I find the other two sides, I'm applying that momentum is mass times velocity. I can say PA prime is equal to MA times VA prime, and I can say PB prime is equal to MB times VB prime, and then that's how I would go back and find the velocity of them afterwards. Okay? So again, doing the two-dimensional ones, the key here is the momentum triangle. And knowing that the total momentum before is equal to the total momentum after, but again, because momentum is a vector quantity, you add your vectors head to tail. And once you look at this momentum triangle, then the problem is just easy. This is geometry. And then you just use momentum as mass times velocity to go back to find the velocity. That's it.